Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So it was also here that I took my Bachelor's of Science in Pharmaceutical Chemistry. And today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you had any problems with homework or with tutoring, then check out the links in the description below. Okay, so now we're just going to get started on our first set of questions. Okay, so the first question, I don't know if you can read it, but basically it says to rank the following radicals in order of decreasing stability. And then they just have a bunch of different examples of radicals. So I'm just going to write them all down. Okay. And I'll also write down what affects the stability of free radicals. Okay, so basically this depends on the inductive effect. It also depends on resonance. And also the mesomeric effect. Okay, so electron deficient groups that provide more electron density makes free radicals more stable. Okay, so I'm gonna draw out just like a line graph from the most stable to the least. Okay, so basically our most stable radicals would be the allylic. So I'm gonna draw it out right here. I'll draw the radical up here. So basically allylic radicals are when your free radical carbon is connected to a carbon that is double bonded. and this is the most stable out of the 4. And then the second stable are the tertiary free radicals. Let's do it in a different color. It's because I can. Okay, so the radical is shown here. And a tertiary free radical is when the carbon that contains the radical is connected to 3 other carbons and no hydrogens. And then, as you can guess, the secondary free radicals are next. Okay, so secondary free radicals are when the carbon that has the free radical is connected to 2 other carbons and 1 hydrogen. And then lastly, the least stable free radical is the primary. Just gonna fit it at the very end. Okay, and as you can guess, primary free radical is when your carbon is only connected with 1 other carbon. Now let's look at the answer from our junior tutor. So they have their 1 degree radical allylic, 2 degree, 3 degree. The stability of a radical increases as the number of alkyl groups bonded to the radical carbon increases. The allylic radical is more stable than the other radicals because 2 resonance structures can be drawn. Allylic radical is more stable than tertiary radical, and secondary radical is more stable than a primary radical. Therefore, the decreasing order of stability is as follows. Okay, so that was a very well written solution, and it was also correct. Okay, so now we can move on to question number 2. Which of the following statements about peptide bonds are true? So before I get into reading all of the different options, I'm just going to draw out what a peptide bond is. Just for those of us that aren't familiar with biochemistry. So this is kind of what your amino acids, an amino acid chain looks like. So I'm just going to draw out 2 amino acids that are held together by a peptide bond. So all amino acids have an amino group and then a carboxylic acid group. And then what makes them all different is that they all have different R groups. And what holds them together are these peptide bonds. So it's basically the carboxylic acid end of one amino acid that is bonded with the amino end of a second amino acid. Let's look at A. Peptide bonds are ester linkages. So this is false. They are not ester linkages. You'll see that there is a nitrogen involved. The peptides are polymers of amino acids. So this is actually correct. I'm gonna write it down. C. Peptide bond formation is a hydrolysis reaction. So this is false. It's not hydrolysis. What actually causes peptide bond formation are condensation reactions. A tripeptide contains 3 amino acid residues, so this is actually correct. And then lastly, peptide bonds form from nucleophilic attack by an alpha carboxyl carbon atom on an electron pair of an alpha amino nitrogen atom of another amino acid. So this is correct, where it's formed by a nucleophilic attack. Let's go over them again. So A was false. B was correct. C was false. D was correct. And E was correct. So our junior tutor said peptides are polymers of amino acids. A tripeptide contains 3 amino acid residues. The solution was correct. I'll also add that E is correct as well. Okay, so let's move on to question number 3. Morphine is a weak base. A 0.15 molar solution of morphine has a pH of 10.5. What is Kb for morphine? So let's write out the equation reaction that is involved in this question. So I'm just going to write down the chemical structure of morphine. It doesn't really matter, but it helps us kind of visualize what's happening in the question. Okay, so I have morphine right here. Then it reacts with water. The morphine get protonated. So in this case, since morphine was the proton acceptor, it is the base. Water acts as the acid, making the protonated morphine our conjugate acid, and then the hydroxide ion our conjugate base. Okay, so I am now just going to write out the equation expression to calculate for Kb. Okay, so I did products over reactants. And now I'm just going to draw out an ice table. Okay, so our initial concentration of morphine is 0.15, and then our initial concentrations of our products are 0. Since this is the start of the reaction, they aren't there yet. For the change, it's going to be minus x, and then the change for the products is plus x. And then lastly here, the equilibrium. Okay. So we know that the pH is equal to 10.5. So we can use this to solve for POH since this is a base. So to calculate for POH, it's going to be 14 minus our pH value, which is 10.5. Actually, sorry, it's the other way around. And then we should get negative 3.5. Okay, so since we know the POH, we can calculate for the concentration of our hydroxide molecule, which is going to be 10 to the negative 3.5. So this is because I'm going to write in between why that is. So since POH is equal to negative log of the concentration of OH, Therefore, we can say that the concentration of OH equal to 10 to the negative 3.5. Okay, so then we get a concentration of 3.16 times 10 to the negative 4 molar as our X value. So since we know that, I'm just going to sub it into our ice table. Since it's a monobasic reaction, that is the same. This 3.16 times 10 to the negative 4 will be the same for both the concentration of OH minus and for the concentration of the protonated morphine. Okay, so now that we know what X is, we can sub the concentration values in our Kb reaction equation. So you get 3.16 times 10 to the negative 4 squared all over 0.15 minus 3.16 times 10 to the negative 4. And then our final Kb value should equal 7 times 10 to the negative 7. So let's check out the answer from our junior tutor. Let's label morphine as B to further calculations. Let's write the overall reaction and a ice chat. Okay, so they kind of did the same thing. They have their Kb expression. To get, oh, I know I was right the first time. So yeah, so POH is 14 minus 10.5. Okay, so then they got 3.5 as their POH. And then to find the concentration of their OH minus, they did 10 to the power of negative 3.5, and they got 3.16 times 10 to the negative 4. And then they subbed this value into their Kb expression, and they got the same answer. So this solution is correct. Okay, so now we move on to question number 4. Determine the pH of an HNO2 solution of each of the following concentrations. So this will be similar to what we did in the previous question using ice tables. So I'm just going to write out the reaction that takes place of HNO2 in water. Okay. So now let's write out our ice table. So the initial concentration for A, say this is A, is 0.5 molar. And then we draw it out like this. It'll be 0, 0 for our two products. The change is negative x. These are just positive x. So we aren't taking into account the water since it is a liquid. And then lastly, in the E row, you get 0.5 minus x. And then these two are just going to equal x. So now I'm just going to look up the Ka of HNO2 at 25 degrees Celsius. Okay, so we get it as Ka is equal to 4.5 times 10 to the negative 4. So these values are usually given in like your textbook. And now I'm just going to write out the expression for Ka. So Ka is equal to the concentration of your products. So H3O plus times NO2 minus. All of that divided by the concentration of our reactant. Okay, so we know that the Ka is equal to 4.5 times 10 to the negative 4. And we know that the top two concentrations are the same. They're both x. So when you multiply two x's together, you get x squared divided by the concentration of HNO2, which is going to be the 0.5 minus x. So now I'm just going to simplify this expression, and you'll see that it makes like a polynomial expression. Okay, so it's at this moment where you would use the quadratic formula that they made us all memorize in high school. But once you calculate what x is, just look at the positive value and then you end up with an x value of 0.0148. So from there, the concentration of H3O plus is equal to 0.0148 moles per liter. And then from here, we can calculate the pH just by taking the negative log of this value. And then we end up with a pH equal to 1.8. Okay, so this is for A. So basically you do the same thing for B and C, but I'm not going to write out the whole thing again. I'm just going to write out the pH values that I got. So for B, I got a pH of 2.2 when the concentration is 0.1 molar. And then for C, I got a pH of 2.7. And then this is when the concentration was 1.1 times 10 to the negative 2. So let's see what our junior tutor said. The Ka value of HNO2 is missing in the question. I am taking the value given in the book, which is Ka equals 4 times 10 to the negative 4. So that is similar to what I have as well. And then they wrote out the reaction and they made little ice tables. And then they got Ka equals concentration of products over reactants, G equals to x squared over 0.5 minus x equals to 4 times 10 to the negative 4. Solving the quadratic equation, we get 0.01394. Yeah, so it's the same as mine, except off by a few sig. And then let's look at what they got for B. They got a pH of 2.2, which is the same as mine. And then for C, they got a pH of 2.7. So I'm going to say this solution is correct. Okay, so that was question number 4. And now we are moving on to question number 5. Draw the product of the following reaction. Show all the hydrogen atoms in your structure. Okay, so let me just write this out. Okay, so now I'm just going to write out the definition of the reaction that occurs when H2 is reacted with a metal catalyst such as platinum. It is called hydrogenation. Okay, so I'm just going to write it out. This is when you have the addition of molecular hydrogen to unsaturated molecules in the presence of metal catalysts basically it's the reduction of the double bond. Just to simplify things. And then I'll draw out the final product. Okay, so you can see that these two new hydrogens were added from here. We have the double bond that is now a single bond, and we ended up with butane as our final product. Let's check out the answer from our junior tutor. The alkene is reduced to butane. Okay, pretty simple question. So the solution is correct. Okay, so now let's move on to question number 6. Add formal charges as necessary to the following structure. All unshared valence electrons are shown. What is the overall charge on the species? So let me write down this species. Okay, so now I'm just going to write out the equation for formal charge. So, formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. And now we're going to do each atom one by one. So first let's look at oxygen. Okay, so its number of valence electrons is 6. The number of non-bonding electrons, so let's look at the lone pairs right here that aren't participating in the bonding. You'll see that there are 6 of them as well. And then you'll see that there are 2 electrons that are involved in each bond. So I'm just going to divide that by 2. And then we end up with a formal charge of -1. So I'm just going to write the charge in for the oxygen. Now let's look at the nitrogen. So for the formal charge of nitrogen, nitrogen's valence electrons are only 5. If you look at the structure, you'll see that there are no non-bonding electrons. So I'm just going to write 0. And then if you count how many electrons are involved in the bonding, so in all the bonds, each one it has 2, and there's 4 of them. So there are 8 bonding electrons divided by 2. So basically it's 5 minus 4. And then nitrogen has a +1 formal charge. So I'm also going to write that in. So everything makes sense so far, but I'm also going to do the formal charge of carbon just for good measure. So for carbon, there are 4 valence electrons. There are no non-bonding electrons. And then the number of bonds to carbon are 4, so there are 8 bonding electrons involved divided by 2. So you end up with 4 minus 4. So the formal charge on carbon is 0. And the overall charge of our species is just going to be neutral, so it'll be 0 as well. That's because the oxygen is -1 and the nitrogen is +1, so they cancel each other out. Okay, so let's look at the answer from our junior tutor. Okay, so it looks like they calculated the formal charge of ozone. So the work looks correct, but for this question in particular, it is incorrect since it's a different structure altogether. So I'm just going to write out what I did. Okay, so I wrote out the formal charge of oxygen is -1, formal charge of nitrogen is +1, formal charge of the carbons is 0, where formal charge is equal to valence electrons minus non-bonding electrons minus bonding electrons divided by 2, and then the overall charge of the species is 0. So the work was right, but it wasn't for the question that was asked. Okay, so now let's go on to question number 7. Predict the products when 1-propanol is heated in the presence of H+, I'm assuming. Include all hydrogen atoms in your structure. Show both the organic and the inorganic product formed in this reaction. So it looks like this person attempted to write out an answer, but it probably wasn't right. So let's try to look at the reaction that is given. They had 1-propanol with sulfuric acid. and a catalyst. Okay, so I'm gonna write out the structure of 1-propanol. That is when you have an alcohol group on carbon 1, and there are 3 carbons in the structure since it's propanol. So basically, when you have an when you have an alcohol heated in the presence of H plus, you have the elimination of your alcohol group. So you have the elimination of your OH with the heat. So this forms a double bond in our final product. I don't know why I wrote it out twice, but basically gonna give out the same answer anyways. So now we have a newly formed double bond with the elimination of our alcohol group, and water was formed. So the name of this new product is Prop 1 ene. Okay, so it looks like the person that asked the question had the right idea drawing out the double bonds with water, but they just had like way too many carbons involved. Let's look at the answer from our junior tutor. Oh, they have the mechanism shown here. So they have the 1-propanol reacting with the acid to give, yeah, the 1-propene is also correct as a name, plus water. And then they have the mechanism. So I didn't draw it out, but basically one of the double bonds of oxygen comes and deprotonates one of the acids. Then from there, the oxygen has a positive charge. And then the bond comes and kicks it off, forming water. And then from there, one of the hydrogens comes down to neutralize that positive charge. And that's how you get the double bond, the 1-propene. So this answer is correct. Okay, so I think we have room for one more question. In the box below, draw the structure of the organic product of this reaction. Okay, so we have it's question 8. We have a double bond here. Okay, so this osmium complex, I'll draw out the mechanism, looks like this. And basically, there's like a movement of electrons that occurs once it reacts with the double bond. And the movement kind of looks like that. And this is called a syn addition. So this is our starting product, but now you can see there are new bonds to the two oxygens. I'll show the hydrogens as well. And then you can see it's still connected to this osmium complex. But then finally, this is when the sodium bisulfate comes in. And it removes that osmium group. And then our final product is a cis-diol. Let me draw out the stereochemistry. So the oxygens are on the same side, and then the carbons both go up as well. And then this is called a cis-diol. So it's called cis since they are on the same sides. And then the di means there's two, and then the ol means there's two of the alcohol groups. So let's look at the answer from our junior tutor. Ooh, okay. An alkene can be oxidized with osmium tetroxide to form 1,2-diols. This diol can also be called a glycol. Alkenes react with the osmium tetroxide to form cyclic intermediate called osmic ester. Due to the osmium are in highly positive oxidation state, so it attracts ions. So because the osmium is in a high oxidation state, that's what causes all those movement of electrons. And then the formation of the cyclic intermediate is syn addition because both oxygens are delivered to the same side of the double bond. So oxidation of osmium tetroxide is a stereoselective reaction, so cis-diols are formed. Let me just erase this E. I probably spelled it wrong. Cis-diol, that makes more sense. Cis-diols are formed. And then they have the reaction, where you have your cis-2-butane reacting to get your syn-diols. And then again, they have the same mechanism, syn addition. And then they show the cyclic osmic ester intermediate right here. And then finally, the osmium is removed to get your final product. Oh, nice. So this tutor went... Oh, is there more to the question? Okay, so yeah, so they're going to draw all the different stereoisomers that were involved if you have a racemic mixture. So basically they have the mechanism again, but this time they draw it in a way so that we can see the stereochemistry like this. Both are mesoform, So here again, you can see the cyclic rotation of the molecules, converted Fisher diagrams, and then you'll see the racemic mixture. So the left is the positive, and then the right is the negative. Wow, so that was really, really well written. So this solution was correct. Okay, so that brings us to the end of today's Q&A session. So if you like today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description below. Also, if you like today's video, please give it a thumbs up and also leave a comment. And don't forget to share it with all your friends and fellow classmates to learn more about chemistry. So this has been Donna from OneClass, and I hope to see you soon. Bye.